Okay, so what's the probability you think that walking down the street you'd see a pink elephant? Is it 1/2? Because, well, you either see pink elephant or not. Your sample space is of size 2. Well, therefore, wouldn't you have probability 1/2? Well, let's extend our definition of probability to make sense of this puzzle. It's entirely possible, and this is what happens in general, that even though you will have a set of outcomes, not all outcomes are the same. Some outcomes are more likely than others. For example, you might have a bias coin, which comes up heads a lot more than comes up tails. And even though both heads and tails are outcome, they're not really equal. Similarly with pink elephants, maybe the probability of seeing a pink elephant is non-zero and goes up even higher on Halloween, but I wouldn't say that you're as likely to see a pink elephant on George Street as you're likely not to see it. So for that we use the term probability distribution, and here let's just define a probability distribution on a finite set. Again, you'll have enough probability statistics of continuous distribution later on in the respective courses. And let's just say that the function is a probability distribution just if it satisfies two properties. So it's defined on a set, so it's a function from a set to real numbers. And for any outcome, any element of the set, the function takes value between 0 and 1. And moreover, if you sum up the values of your probability distributions over all elements in the set, you get a 1. So for example, if you have two coins and one of them comes up with a value 1/2 and another comes up, and heads, if you have a coin and comes up heads with probability 1/2 and tail with probability 1/2, you just map the two outcomes to the number 1/2, and the sum of the two 1/2 plus 1/2 is equal to 1. So this particular distribution that we talked about before, when probability of an element is just 1 over the size of the set of the outcomes, is called the uniform distribution. And you'll probably see people saying, select something uniformly at random. That means with the equal probability to any outcome. And oftentimes when people say select randomly, they actually do mean uniformly random. So fair coin, tossing a fair coin is assumed to be uniform distribution over the outcomes. Heads and tails would come up with probability 1/2. That's what makes it fair. But let's say we have a bias coin, and in this case, for example, we may have heads, for simplicity of calculation, coming up twice as much as tails. So in this case, our probability function that maps heads and tails to real numbers will assign the number 2/3 to heads and 1/3 to tails. You see they still sum up to 1, and both of them are between 0 and 1. But now those numbers are different. So now let's redefine in a more general setting the probability of an event. Before we say the probability of an event is just the size of the event over the size of the sample space. But now, since different elements in A and different elements in S have different probabilities, we will just define the probability of an event as a sum of the probabilities of outcomes in this event. And again, we still have the feature that because every probabilities of all the events in sample space sum up to 1, probability of event not happening is 1 minus probability of an event happening. And this definition can let us do other things. For example, probability of event A or event B happening is the probability of A plus probability of B minus probability of both of them happening, because we counted it twice. You've seen it before when we did set theory and when we did inclusion-exclusion. So a useful kind of events is when two events are disjoint. That is when the set A and the set B don't have any element in their intersection. For example, if you throw dice, if one event is that both come up even, and another event is that, let's say, both of them come up 3, well, those are two disjoint events, because if they come up both even, they don't come up both 3, and vice versa. And this is defined for 2 events, but you could define it for more than 2 events, and in this case you need to be a little bit careful, because there is the notion of pairwise disjoint, when every 2 events their intersection is empty, and there is a more general notion when events are mutually disjoint, so that every subset of events has an empty intersection. Okay, so let's try to do a little bit probabilities in this non-uniform scenario. So suppose you're throwing dice, and just one die, and it's biased so that 3 appears twice as often as any other number. Again, this is just a simple example. It's not like this is exactly what you're going to see in the biased dice. So let's figure out probabilities of all the events in the sample space. So the sample space is still the die coming up 1, 2, 3, 4, 5, or 6. In this case, since 3 appears twice as often as any other number, you could work out the equation and see that it works when probability of 3 is 2/7 and probability of all the other dice are 1/7. Well, that's because the probability of, so if you assign the number 2, so if you sum up 2 and 5 ones, you get a 7, so the total sort of sum is a 7, so you could calculate the probability now as 2 in respect of 1 divided by the total, that's 7. So if this is your biased die, what is the probability of an event that an odd number appears? So what the event is that either 1 appears, or 3 appears, or 5. Probability of getting a 1 is 1/7, and so the probability of 5, and probability of getting a 3 is 2/7. So probability of the event that an odd number appears is 4/7, which is a little bit more than the 1/2 that we would get if the die weren't biased. So what is the probability that or of 2 events appear? So either an odd number or a number divisible by 3, or it can be a number that's both odd and divisible by 3, by 3 itself. So the event A consists of 1, 3, and 5. Event B consists of 3 and 6. Their intersection is 3. We just calculated the probability of A is 4/7. You could calculate the probability of B 3/7 because it's 2/7 plus 1/7. Probability of A intersect B is 2/7. That's just the probability of getting a 3. And now by that formula that we just had, by the principle of inclusion-exclusion, we get the probability of getting an odd number or a number divisible by 3 is 5/7. And intuitively this makes sense because this is probability of getting 1 or 3, 5 or 6. Okay, so here's something to think about for next time. Suppose you have a bunch of people in the room and you're trying to figure out the birthdays. What is the probability? So how many people should be in the room so the probability that at least 2 of them have the same birthday, have birth on the same day, is at least 1/2. So think about it and try to figure it out. Hint, probability of a person having a birthday on any specific day is pretty small. It's 1 over 365 or 366 if you have a leap year.